Lesson 10-6. Find segment lengths in circles. By the end of today's lesson, we'll be able to successfully find segment lengths in circles. Now, for the first vocab term, segments of a chord. When two chords intersect in the interior of a circle, each chord is divided into two segments. So if we have a circle, and we have two chords that intersect, then these chords are cut into segments. And the secant segment will refer to a segment that contains a chord and then has exactly one endpoint outside the circle. So this would be a secant segment. And then the external segment will be part of a secant that is outside of the circle. So this part is called the external segment. We actually have another vocab term called the tangent segment. The tangent segment is just another possible segment that intersects one point on the circle and possibly another secant segment at one point. Or it can also intersect another tangent segment. Theorem 10.14, segments of chords theorem, states that if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one circle is equal to the product of the lengths of the segments of the other chord. So what this means is that if you're given two chords A, B, and C, D, then EA times EB would equal to EC times ED. Now to prove this one, I will just quickly go over it, and then for the full proof it's on my website, and I can draw the auxiliary lines and connect CB and AD to form two similar triangles. And how are they similar is that they have a pair of congruent vertical angles as well as another pair of angles that are equal to each other because they share the same arc by theorem 10.8 in lesson 10.4. So now that I have two pairs of congruent angles by AA similarity postulate, these two triangles are similar. So if I set up a proportion AE or EA to EC, because these two sides correspond to each other, and ED to EB, and then I can move AB to this side by multiplying by both sides, and then EC. So this gives me the proof. Okay, I just multiplied it EB to both sides and then EC to both sides. So for the full proof again, it's on my website. And now let's do an example. Find ML and JK. So I'm going to set up my formula here. So I will do MN times NL equals to NK times NJ. So MN is x plus 1, NL is x plus 3, NK is x, and J is x plus 5. So I can go ahead and solve this using algebra. And then x would equal to 3. So ML would equal to x plus 3 plus x plus 1, which is 10. And then JK we go to x plus 5 plus x, and x is 3, 11. Theorem 10.15. Segments of secants theorem. If two secant segments, such as EB and ED, share the same endpoint outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. So that means this external segment EA times the secant segment EB will equal to the external segment EC times the secant segment ED. To prove this theorem, you will also have to draw in auxiliary lines CB and AD so that you can prove that these two triangles are similar by AA postulate to find this relation. You may pause the video and refer to my website for the full proof right now, and I will also explain the proof in class. So example 2, find the value of x. Now I can use the formula 6, the external segment, 2, or times 6 plus 4, which is 10, equals 5 times 5 plus x. So this would be 60. And 5 plus x would equal to 12. X would just equal to 7. And then for example 3, find the value of x, so we can apply theorem 10.14 again for as extra practice. So 5 times 12 equals 6 times x, and x just equals to 10. And again, theorem 10.15, 6 times 6 plus 8, which is 14, equals 7 times 7 plus x, 4 equals 49 plus 7x, and then x minus 49 should be 5. Theorem 10.16, segments of secants and tangents theorem, states that if you have a secant segment such as ED and a tangent segment such as EA, and they share an endpoint outside a circle, then the product of the lengths of the secant segment, meaning ED here, and its external segment, EC, so the product of the secant segment and the external segment is equal to the square, the length of the tangent segment EA. To prove this theorem, you will have to draw in auxiliary lines AC and AD to establish two more similar triangles. And we can prove that these two triangles, AEC, is similar to triangle DEA by AA similarity postulate. And again, we can establish a proportion where EA to EC, so EA to EC equals ED to EA, E long side to short side. So cross multiply EA squared, EC times ED. So that's where it comes from. And for the full detailed proof, if you're interested, you may pause the video and refer to my website right now, and I will still explain it in class one time. And now let's first look at how to apply the theorem. Example 4. Use the figures below to find RS and JK. So I can go ahead and square 14 squared and then set that equal to 12 plus x. Okay, so remember we want to multiply the entire secant segment by the external segment. So 14 squared is 196, 12x plus x squared. And then we can go ahead and use the quadratic formula because you can't really factor this one. So that would be and once this is simplified, x should be equal to -6 plus 2 square root of 58. And that is about 9.23. And you would ignore the other answer because it would be a negative number. Okay, let's do another practice. And it's exactly the same way. You take the tangent segment, square it, which is 8 squared, and you set it equal to x, which is the external segment, times the entire length of the secant segment, x plus 6. And now you're going to end up with a polynomial again. And for this one, you also can't factor, so you're going to have to use a quadratic formula. So -6 plus or minus 6 squared minus 4ac. And you should end up with -3 plus or minus, but we only want the plus. So you can go ahead and leave it in simplest radical form if I ask you to, or decimal form if you get to use a calculator for the test. Example 5. You are standing at point C, 45 feet from Point State Park Fountain in Pittsburgh, Pennsylvania. So this is 45 feet here. The distance from you to the point of tangency on the fountain is 105 feet. So from point C to point D, 105 feet. Find the distance CA between you and your friend at point A. So you want to find this one. So again, you will have to use theorem 10.16. We can set it up as CB times CA. So CB times CA will equal to CD squared. CB, we know it's 45. CA is what you want to calculate. CD is 105 squared. So CA, and once you simplify this, should be 245 feet. Example 6. In example 5, suppose AB, segment AB, is the diameter of the fountain. Use the diagram below and theorem 10.16 to find the radius of the fountain. Well, in example 5, we already used theorem 10.16 to find CA, which is 245 feet. Then we know that CB is 45 feet. Then we subtract this, we can get, subtract CB, we can get the diameter AB, which is 200 feet. And taking 200 and you divide by 2, that will give you the radius of 100 feet.